Today's topic is Compton effect, in which we will discuss about the X-ray scattering. Myself, Dr. Akhilesh Jadhav, Government J. Yoganandam, Chhattisgarh College, Raipur. My lecture contains the following key points. First is introduction, then theoretical explanation. Next is Compton's experiment and its explanation. Then comes application, and in last we will discuss about conclusion. So let's start with introduction. First, I will discuss about brief overview of the Compton effect. Compton effect was discovered or first observed by Arthur Hawley Compton in 1923 and further verified by his graduate student Y. H. Wu. And for this achievement, Compton received the Nobel Prize for Physics in 1927. The Compton effect plays a crucial role in the development of quantum mechanics because it illustrates the particle-like behavior of photons or light quanta. This effect is also known as Compton scattering. Key concepts of the Compton effect are: first is scattering of X-ray. The Compton effect involves the scattering of X-rays or gamma rays by electrons. X-rays and gamma rays contains high energy photons. When these high energy photons collide with electrons, the photons are deflected and their wavelength changes. Now, second key concept is change in wavelength. The most significant aspect of the Compton effect is that the wavelength of the scattered photon is longer, or in other words, the energy is lower than the original incoming rays. This change in wavelength is directly related to the angle at which the photon is scattered. Third key concept is Compton formula. The relationship between the change in wavelength and the scattering angle is given by the Compton formula. Let the wavelength of incoming rays say lambda 0 and wavelength of scattered rays is say lambda dash. Then the difference between these two wavelengths, that is del lambda is equal to del lambda is equal to lambda dash minus lambda 0. Here the difference between lambda dash and lambda 0 is known as wavelength shift del lambda. It is also observed that the wavelength shift depends upon scattering angle theta. After simple calculation, the Compton formula may also be given by del lambda, that is wavelength shift, equal to lambda dash minus lambda 0 equal to h over MEC into 1 minus cos theta, where Me is the mass of electron, c is the speed of light, and theta is the scattering angle of the photon. It is observed that wavelength shift del lambda increases with the increase of scattering angle theta. It is also observed that the wavelength shift del lambda is independent of the wavelength of the incident beam, and the scattering material is dependent on the scattering angle theta. Fourth key concept is energy momentum conservation. The Compton effect demonstrates the conservation of energy and momentum. When a photon collides with an electron, energy and momentum are transferred between the photon and the electron, which results in the change in the photon's wavelength and the recoil of the electron. Fifth key concept is quantum mechanical explanation. The Compton effect supports the quantum theory of light, where light is described as particles, that means in terms of photons, with quantized energy. It shows that photons have momentum and can interact with matter in a way similar to particles. And the last key concept is impact on physics. The discovery of the Compton effect provided strong evidence for the quantum theory of light and the concept of photons. It helped to validate the idea that light can exhibit both wave-like and particle-like properties, a key aspect of quantum mechanics. The Compton effect is a fundamental phenomena in physics that provides crucial evidence for the quantum theory of light and highlights the dual nature of electromagnetic radiation. Now I will show the importance of Compton effect in quantum mechanics and particle physics. The Compton effect, also known as Compton scattering, is significant in both quantum mechanics and particle physics. First, I show you the importance in quantum mechanics. First importance is wave-particle duality. The Compton effect provided critical evidence for the wave-particle duality of light. It demonstrated that light could behave not only as a wave but also as a wave particle in terms of photon. When X-rays are scattered off electrons, the shift in wavelength can be explained only in light is treated as a collection of particles. Second importance is energy and momentum conservation. The Compton effect requires the application of conservation laws of energy and momentum to photons and electrons. This process reinforces the idea that photons, despite being massless, carry both energy and momentum, a key concept in quantum mechanics. Third importance is photon theory of light. The effect directly supports the photon theory of light proposed by Einstein. The experiment showed that photons could impart momentum to electrons, causing the electrons to recoil. The wavelength shift observed in the scattered X-ray directly correlates with this momentum transfer. Now it's a time to discuss the importance of Compton effect in particle physics. First importance is about the understanding fundamental interactions. Compton scattering is a process that involves the interaction between photons and charged particle. This interaction is fundamental to many processes in particle physics, including the analysis of high energy collisions and the study of cosmic rays. Second importance is about the understanding particle detectors. Compton scattering is used in the detection of gamma rays and X-ray in particle physics experiments. It is one of the key mechanisms by which these high energy photons lose energy when passing through matter, and understanding this process is crucial for designing and interpreting the result of detectors. Third importance is implication of quantum electrodynamics, that is QED. The importance is the Compton effect is also important in the context of QED, the quantum field theory describing how light and matter interact. It provides a simple example of the interaction between charged particle and electromagnetic fields, which is described by QED. The Compton effect bridges classical and quantum physics by showing how energy and momentum are conserved in photon-electron interactions. It has become a cornerstone in one understanding of quantum phenomena and the interactions of particles, contributing significantly to the development of quantum mechanics and particle physics. Now I will explain the theory behind this effect. The theoretical explanation of the Compton effect is rooted in quantum mechanics and relativistic physics. Let's look into how the Compton effect is explained theoretically. For this we discuss about quantum theory of light. In quantum mechanics, light is not only a wave but also consists of particles called photons. Each photon has energy E equals to h nu, where E is the total energy of the photon, h is Planck's constant, and nu is the frequency. Photon also have momentum given by de Broglie equation, that is P equal to h over lambda, where lambda is the wavelength of the photon. Relativistic momentum and energy conservation laws plays important role to understand the theoretical explanation. It is important that when a photon collides with an electron, the total energy and momentum before and after the collision must be conserved. Let before the collision, the system consists of photon with energy E naught and momentum P naught, and a stationary electron with rest mass energy E equal to MEC square, where Me is the electron mass and C is the speed of light. After the collision, the photon is scattered with the reduced energy E dash and altered momentum P dash, and the electron recoils with the some kinetic energy square root of Pe C square plus M2 C square whole square and momentum Pe. The energy conservation in this process is given by following equation: E0 plus MEC square is equal to E dash plus square root of PEC square plus M2 C square whole square. The Pe is the momentum of the recoiling electron, and the momentum conservation is given by P0 equal to P dash plus Pe, where P0, P dash and Pe are the momentum of incident photon, scattered photon and recoiling electron. By solving this equation and simplifying, we get the Compton wavelength shift formula: del lambda is equal to lambda dash minus lambda naught equal to H over MEC, and in bracket 1 minus cos theta. Now we will discuss about the physical interpretation. Let's start with the scattering angle. The change in wavelength depends on the angle theta at which the photon is scattered. The greater the scattering angle, the larger the change in wavelength. Now discuss about energy transfer. The Compton effect shows that a photon can transfer part of its energy to the electron. This energy transfer results in a reduction in the photon energy and hence an increase in its wavelength. Let's see what about photon momentum. The photon momentum before and after the collision changes, reflecting the momentum transferred to the recoiling electron. This change is crucial for understanding the interaction in terms of relativistic mechanism. The theoretical explanation of the Compton effect combines quantum mechanics and relativistic mechanics. The interaction is described as a photon colliding with an electron, transferring energy and momentum and resulting in a change in the photon's wavelength. This explanation confirms the particle nature of light and demonstrates the conservation laws in action, validating the principles of quantum mechanics and relativistic physics. Now in real matter, electrons are not stationary. Actually, they are moving somewhere in the crystal or around the nucleus. If the initial kinetic energy of the electron is small compared to the energy of the incoming photon, the equation which I showed you will describe the situation well. Now we will discuss about Compton experiment. The schematics of Compton's experiment setup are shown in figure. The idea of experiment is very simple. Monochromatic X-ray and wavelengths lambda naught are incident on a sample of graphite which is known as target, where they interact with the atoms in the target sample. The latter emerge as a scattered X-ray with wavelength lambda dash. A detector placed behind the target and measure the intensity of radiation scattered in any direction theta, where theta is angle between the direction of the scattered beam and the direction of the incident beam. This angle is known as scattering angle. In this experiment, we know that intensity and wavelength lambda naught of incoming X-ray. Now, by measuring the scattering angle theta, we can calculate the intensity and wavelength lambda dash of a scattered X-ray. Typical results of these measurements are shown in figure, where the x-axis is the wavelength of scattered X-rays, and the y-axis is the intensity of the scattered X-rays measured of different scattering angle theta indicated on the graphs. For all scattering angles except for theta is equal to 0 degree, we measure two intensity peaks. One peak is located at the wavelength lambda naught, which is the wavelength of incident beam. The other peak is located at some other wavelength lambda dash, which is the wavelength of scattered light. We can see the two peaks are separated by dem lambda, which the difference of lambda dash and lambda 0. That is del lambda is equal to lambda dash minus lambda 0 equal to h over m naught c in bracket 1 minus cos theta. The factor h over m0c is called the Compton wavelength of the electron, which is denoted by lambda c. Now we will discuss about applications of Compton effect. Compton effect has several important applications across various fields. Let's discuss one by one. First, in medical imaging and diagnosis. The Compton effect is utilized in CT scanners to enhance imaging techniques by understanding how X-ray photons scatter. Medical professionals can improve the resolution and accuracy of CT scans. Second, in radiation therapy. In cancer treatment, Compton scattering helps in dose calculations and understanding how radiation interact with tissues. Third is material science. Material analysis. Compton scattering is used to study the atomic and electronic structure of materials. It helps in understanding the properties of materials at the microscopic level. Non-destructive testing means NDT. This technique is used to inspect the integrity of materials and structures without causing damage, such as in welding inspection or evaluating the quality of composites. 4. In the field of astrophysics. The Compton effect is crucial in gamma ray telescopes like the Compton Gamma Ray Observatory to study high energy processes in the universe. It helps in analyzing the high energy photons emitted by celestial objects. Fifth, in the field of cosmic ray studies. Understanding Compton scattering helps in analyzing cosmic rays and their interactions with the Earth's atmosphere. Sixth is in nuclear physics. Photon-electron interactions. In nuclear physics research, Compton scattering helps in studying the interaction between photons and electrons, which provides insights into the structure of atomic nuclei. Seventh, in environmental science. Radiation detection and monitoring. Compton scattering is used in radiation detectors and monitoring system to measure the analyze environmental radiation levels, such as in tracking radioactive contamination. 8.1 is in the field of fundamental physics. And last one is the testing quantum electrodynamics, QED. The Compton effect provides a way to test and verify aspects of quantum electrodynamics, a fundamental theory in physics describing how light and matter interact. Overall, the Compton effect is a key tool in both theoretical and applied sciences, helping to enhance our understanding and capabilities in various domains. Now, in the last of my lecture, we will conclude. As it has been such a significant finding, the Compton effect might be considered to be one of the cornerstone of quantum physics. The Compton effect or Compton scattering has several key conclusions and implications. Now, I conclude point-wise. First point is photon-electron interaction. The Compton effect demonstrates the X-ray or gamma ray photons can scatter off electrons, resulting in a change in the photon's energy and direction. This interaction is consistent with the principles of quantum mechanics and the particle-like nature of light. Second point is quantization of energy. The change in photon's wavelength during Compton scattering depends on the scattering angle. This quantized energy shift provides evidence for the photon as a quantum particle with discrete energy levels, supporting the concept of wave-particle duality. Third point is the confirmation of quantum theory. The Compton effect provides empirical support for quantum mechanics, particularly for the concept of photons interacting with particles like electrons. It validates the idea that photons have momentum and energy, which can be transferred to electrons in a scattering process. Fourth point is scattering theory validation. The observed results of Compton scattering match theoretical prediction made using quantum electrodynamics and special relativity, confirming the accuracy of these theories in describing photon-electron interaction. Fifth point is application in technology and research. The understanding of the Compton effect has led to practical applications in various fields, including medical imaging, that is in CT scans, material sciences, that is non-destructive testing, and astrophysics, that is gamma ray astronomy. It also plays a crucial role in radiation safety and detection. Sixth point is energy and momentum conservation. The Compton effect illustrates the conservation of energy and momentum in photon-electron interactions, reinforcing fundamental principles of physics. The shift in wavelength can be quantitatively explained by these conservation laws, demonstrating their applicability in quantum process. Its study has depended on understanding of particle physics and has a practical impact on various scientific and technological domains. Prior to Compton's discovery, the behavior of photons was primarily understood in terms of wave theory. Compton's experiment provided evidence for the quantum nature of light by demonstrating that photons have both wave and particle characteristics. In summary, the Compton effect is a pivotal phenomenon that underscores the dual nature of light, supports quantum mechanics, and has broad implication and application across science and technology. Now, an interesting question is that what is the difference between photoelectric effect and Compton effect? The answer is the photoelectric effect happens in the bound electrons, while Compton effect happens in free and loosely bound electrons. Second, in the photoelectric effect, a single electron absorbs the entire energy of an incident photon, but in the Compton effect, the incident photon only transfers a portion of its energy to one electron. Another interesting fact about Compton effect is that the scattered X-ray have longer wavelengths than the incident X-ray, and this shift in wavelength is directly related to the scattering angle. This observation could only be explained if light is considered as discrete packets of energy or photons which collide with electrons in a way analogous to billiard balls. This result supported the quantum theory of light and was a crucial piece of evidence of the development in quantum mechanics. So, the Compton effect was pivotal in demonstrating that electromagnetic radiation has a dual nature, exhibiting both wave-like and particle-like property. Thanks to all for watching this video.